In this video, we're going to take a look at some of the important theorems and results that we can conclude when working with power series and their representations of different functions. In the last video, we looked at an example where we took two different series and added them together to make one modeling series for a complicated g of x function. It's what we did back here on example number 3. Now, when we take a look at the basic idea behind what we were using, we were doing something like this. We have a theorem here about adding and subtracting power series. Here's what it says. Suppose that we have a power series that has some coefficients, some x's raised to n's, and again could be centered anywhere. And we have another series that maybe operates the same but might have different coefficients. Now, let's suppose that each of these converge. They model a function f and g respectively. So maybe it's the case that this first one up here converges to f, but the second series over here, this one converges to g. Okay? And they converge respectively to those guys on a common interval. Okay? So maybe there's a common interval I where both of these two things actually converge. Okay? Then it's totally possible to say that if I was to kind of take these two series and add them together, notice that if I was to add the two inside formulas, they would both have this x minus x naught to the nth power in common. And so if I factor that out, I would be left with this. And this here is kind of a hybrid. This is like the blue thing plus the red thing. And this is a new polynomial, and it would converge, well, to the sum of those two original functions. And the same thing actually holds when you deal with subtraction. That if I was to add two power series together, I add the two functions that they model together. Okay? So we can do a lot more operations besides just addition and subtraction. In fact, up here in the note, I see that you can do things like multiplication of these power series and division, but we won't really be spending a lot of time on that or really taking a look at much of it at all. However, there is one other set of operations that we are interested in doing with power series besides adding and subtracting them, and has a very important purpose. If you take a look at the next page in the next theorem, we'll see that we have the following. If a power series, again centered at x0, and has coefficient c sub n, let's suppose it has a radius of convergence. Remember that our options for when a power series converged were always on some interval containing the x naught, at just the x naught, or at every possible value. So here we're going to assume, let's just pretend there's only some radius of convergence. You can only go so far away from x naught and still have this model something. Then, the function that is defined by this particular power series is going to be differentiable on that given interval, and we can state more. In fact, we're going to state two different things here. Here's the first thing that we'll state. We'll actually state that if I wanted to say, again, that I have an f of x function that's modeled by our power series, and now I want to know what's the derivative of that function. Well, obviously, I can just use Calc 1 to find the derivative. That's not too tough. But how would I find what models the derivative? Can that be done? Can I find a power series that models the derivative? Well, surprisingly, that's easy to see that we could just kind of go ahead and rewrite this in the following way. It would look exactly like this. Now, you might be wondering where I'm getting these values from, but actually, this is designed to be a super simple idea. This right here is actually the same thing as saying, I'm going to take each of the terms in my power series, and I'm going to take their derivative. If this guy is just a big, long polynomial thing that looks like c0, c1 x minus x naught, plus c2 x minus x naught squared, and so on, then by taking its derivative, we should get something like this. Notice the derivative of c0 would just be 0, so it disappears. The derivative of c1 times this x minus x naught is just going to end up as c1. The derivative of what I have over here is going to be bring the 2 down, then I'll get my c2 and x minus x naught to the first. And you see that's exactly what I'm writing out up here. In general, it means that I kind of had to take the derivative of this power series. So notice that in order to do that, I would have to say, in general, the pattern is you bring the power down to the front, and then you lower the power by 1, right? I'm just using the power rule every time. The only thing that I can also state here is that since my constant C0 is going to disappear, I can actually start this now at the value of 1, because I don't have a 0th term anymore. So this here is the kind of compressed form of what I have in this expansion. And so this is a power series that will model my f prime. So okay, so that's pretty cool. I can find a function that has a matching power series. If I take the derivative of the function, I kind of take the derivative of the power series. And those things also model each other. Well, if I can take derivatives, the next question might be, can you take antiderivatives? And the answer here again is yes, absolutely. You would just have to take the antiderivative of this big polynomial thing. Now, to start off my antiderivative, I'm first going to think about an important fact with every antiderivative that's in every indefinite integral or antiderivative. Remember that when I do an antiderivative in general, typically at the back of what I'm working with, I always need a plus c, right? If I'm working with something like what's the antiderivative of 2x, then my answer is always something like x squared, but oh, plus a constant, that could possibly be there. And so what I'm going to take a look at right now is that starting constant value. And so I'm going to say that when I take my antiderivative of my green stuff up here, I'm definitely going to get a plus c. But I'm going to put that right at the front so I don't forget to write it. When I look at all of my other stuff up here, I can actually go ahead and write down its antiderivative in the following way. I'll get a c times an x minus an x0. I'm going to go ahead and kind of add in this extra x minus x0 here. It's not really an issue because when I distribute here, this c0 times the negative x0 is just going to combine with the c and make some other new constant. Notice though, as I continue to work down the line, I'm going to have to do something like c1 over 2, x minus x0 squared. Then I'm going to have to do something like c3 over 3, x minus x0 to the third, and kind of so on and so forth. In general, I'm doing an antiderivative of the original series that I had. Of course, I just have to be careful to keep in mind that I have my plus c at the front, and then my series starts. Notice here, I can still start at n as 0 because I didn't lose any of my terms. They all just kind of grew extra stuff, but none of them disappeared. So here, notice that the general pattern was I take my c sub n and I divide by 1 bigger than what the power used to be. So I'm kind of raising my power by 1 and then dividing by my new power. So another way that I could possibly express this, and what you'll see me write it as more typically, is something that looks like this. I'll often just go ahead and rewrite this as c sub n x minus x naught to the n plus 1, and I'll just imagine this whole thing being divided by n plus 1. So again, I've been able to take a series that I already had and a function that was already being modeled by that series, and I was able to now find models for its derivative and models for its antiderivative, just by taking derivatives and antiderivatives of the original power series. Now, one important thing that we might ask is, at the beginning here, we could probably see that these two functions that we had, or this function and this power series, were equal, but they weren't necessarily equal all the time. They were only equal on a given radius of convergence. And so I might want to know, when are these things going to be equal? When is the derivative equal to its power series? And when is the antiderivative equal to this power series? Well, there's an important note for that. We write it like this. We say here that the radii of convergence of the power series in 1 and 2 are both r. So that means that the radius of convergence for the original function and power series remains unchanged when I take derivatives and antiderivatives. So this is really, really powerful. And if you take a look at the note that we have near the bottom, it says that this theorem then ultimately is saying that we can take the derivative of a power series or its antiderivative pretty much like as many times as we want, as many times as we're capable of continuing to calculate each of those respective things. So in the next couple examples, we'll see how exactly we can utilize this to find some power series for some new kinds of functions.